Welcome to the second video. Realizability is defined as follows. A system is physically realizable if it can be implemented by using available information only. Okay, so from a mathematical point of view, if you have a transfer function for your LTI system, the highest order of the numerator polynomial m, if it is less than or equal to n, which is the highest order of the denominator polynomial n, then we call that transfer function to be proper. If m is strictly less than n, then the transfer function is said to be strictly proper. So based on this definition, for a system to be realizable, the transfer function should be at least proper. Okay, so the m should be at most equal to n. It can never be greater than n. So let me just say a few words about what this really means. Okay, so if this is your transfer function, power n plus, and then this is power n. You have two polynomials like that. N cannot be greater than n. Well, let me just give you an example. Well, consider an ideal differentiator. So you have an input u, and let's say the output of that block is very close to u. So in time domain, we have a differentiation operation here. Okay, so the output u dot is equal to d over dt of the input signal u. So if you take the Laplace transform of this equation, y is equal to s times capital U, and that is equal to U. So from here, the transfer function for this operation turns out to be S. So the transfer function for the differentiator block is equal to S. And if you look at that, there's no numerator, denominator. So which means the numerator is of order 1 and the denominator is of order 0. So this is not proper. So obviously, according to the definition we just made, a pure differentiator is not a realizable system. If you go back to the definition, it should be implemented by using available information only. So if it's not realizable, it cannot be implemented by using available information only. And you can actually see that in differentiator, because if you want to take the derivative of a signal, well, if you remember the definition of differentiation, d over dt, you can write this as the limit as delta t goes to 0 of u t plus delta t minus u of t divided by delta t, something like that. Well, if you look at this, to perform this operation, you need to know this u at t plus delta t, but adding delta t to t indicates a future time. So for an exact differentiation, you need to know the future value of the input signal. So I think this is the best example I can give you about this realizability. Okay, so let me just add this as a note here. Differentiation operation requires knowing the future values of the input signal, and hence cannot be exactly implemented in real life. Okay, so what do we do then? Obviously, we need to take derivative of signals. If you consider a PD controller, you need to know the derivative of your error signal. Well, in a practical system, to implement a differentiator, you add a fast pole to that transfer function. So not realizable, but you make it such that you add a pole to that, some time constant tau s plus 1. So this is proper and hence realizable. Okay, well, you need to add such a fastball to your differentiator so that you can actually implement it on a real system. Checking, checking realizability is quite simple. You just look at your transfer function. Obviously, this is true when you have a linear time invariant system. But if your transfer function is proper at least, then you can say that your system is realizable. Okay, but now let me show you an interesting example. Let's just go back to our generic control system block diagram. So let me just clean this up a little bit. Okay, so let me just take this block diagram. Okay, so again, I need to copy it explicitly from this window. I don't know why I have to do that. Okay, so let's take a look at this block diagram. And let me just give you some transfer functions for those blocks. Okay, so let G be represented by this 1 minus S over S plus 2. 1 minus S over S plus 2, which is obviously a proper transfer function. Both numerator and denominator are of order 1. And the control is equal to 1. So this is just a scalar, a static block. Obviously, that's also realizable. Okay, so now let's take a look at the transfer function between the disturbance input D and the control signal U. Okay, so those are two signals in our block diagram, and it's just a good example of how to write transfer functions in an interconnected system like that. Okay, so we don't, I guess, need to go over the details. They're already here in the lecture notes. But you basically write U in terms of D, right? So U is equal to K times E, and then you know how to do it. And if you put in this G and K here, and if you perform the simplifications here, the transfer function from the disturbance input to control signal turns out to be S minus 1 over 3. Well, this is quite interesting because we have a block diagram and it's composed of two blocks. One is, and they're both proper and both realizable. However, when you interconnect those blocks in this particular way, then the resulting transfer function between two signals turn out to be the transfer function is not proper. So that means even though you have individually realizable blocks, when you interconnect in this way, you get a system where an internal transfer function turns out to be not realizable. So this counterexample shows that having realizable blocks does not guarantee having a realizable overall system in general. Okay, so even though checking for realizability is quite simple, when you're dealing with transfer function, when you're dealing with interconnected systems, you have to pay extra attention to making sure that your overall system is realizable. Now let's define some important transfer functions. The sensitivity transfer function and the complementary sensitivity transfer function. Well, for this, we're considering the system with the sensor block being equal to identity. So this is the transfer, this is the block diagram we're considering, except that we're assuming that H is equal to identity. Okay. So let me just bring the transfer function matrix for that system. Okay, and since we assumed H to be identity for this block diagram, you should just not see these H matrices here. So there are no H here. So they are all identity. Okay, so this is the block diagram. Now let's see how the sensitivity transfer function is defined. Is defined as this transfer function I plus gk inverse. Okay, and as you see, I plus gk inverse appears here in several places. Okay, so this is the sensitivity transfer function, and there's also a complementary sensitivity transfer function, and it's such that these two together they complement each other. That means when you take a signal U and pass it through S, you get something. And its complementary transfer function is T. When you pass the same input through T as well, you get something else. And when you add them together, what you get is the same signal that you input to these two block diagrams. Okay. So this transfer function should be, in other words, identity matrix. So we know what S is. So now we can find out what T should be. So this is where we start. S plus T should give the identity matrix. So we know S, so we insert S into there. T is equal to I minus S, and S is given by this transfer function. So you insert that there, I minus that, and we can simplify that a little bit. Instead of the identity matrix, I can write I plus gk inverse times I plus gk. So these two multiplied together will obviously give the identity matrix, right? Okay, so next I can take this into I plus gk inverse parentheses from left. Then when you take this outside the parentheses, I will have I plus gk here. And the second term will just give me the identity matrix. Okay, and this identity matrix will cancel that identity matrix. And in the end, the complementary sensitivity transfer function will be given by this relation, I plus gk inverse times g times k. So with this definition of sensitivity transfer function and the complementary sensitivity transfer function, I can write the output of the system again. Okay, so let me just come back here, and I'm going to write the output y as this transfer function times d, right? And if I come back here, that transfer function is nothing but the sensitivity transfer function times g. So this is S times g times the disturbance input plus this transfer function times the R input, which is the reference input. But that transfer function is exactly equal to the complementary sensitivity transfer function. Okay, so this is T times R. Then I have the same transfer function again, but this time with a negative sign, times W, the sensor noise, minus T times W. Okay, good. Now, if you look at this transfer function here, D is the disturbance input, right? So that is an effect that I don't want. In fact, I want my system in ideal case to reject the disturbance altogether. And what do I want for my control system? I want my control system to track the reference input as closely as possible. So in the ideal case, the transfer function from R to Y should be as close as possible to the identity system. And so this is for good tracking. Okay, for tracking and for disturbance rejection, so disturbance is D, and this should be eliminated. So G is the transfer function for my plant. I cannot change that, but I can play with S. So for good disturbance rejection, I want S to be as close as possible to 0. So the transfer function from D to Y should be as small as possible, which means the sensitivity transfer function should be a lot smaller than the identity system. And this is the third input, the sensor noise. Just like the disturbance, I want my system to be irresponsive to the sensor noise as well. So that means T should also be as small as possible. So for sensor noise rejection, the transfer function from W to Y should be as small as possible, which means T should also be, so that transfer function is the T transfer function that should be as far as possible from the identity system. Okay, so in fact these are already given in the lecture notes, so let me just scroll down here. Okay, so we actually have some conflicting requirements here, right? So in one hand, we want T to be as close as possible to the identity system. On the other hand, we want T to be as small as possible. So if you make it close to identity, you will be achieving your goal for tracking, but that means you will be so that will be against your objective in terms of sensor noise rejection. And for good disturbance rejection, S should also be small. So we want both S and T to be small. However, this is a conflict. There's a conflict here because their sum should be identity. Okay. Well, if you think of these as scalars, then obviously you cannot satisfy these two requirements at the same time. But remember, these are not scalar quantities. These are systems. S is a transfer function, a system represented by a transfer function. T is another system with its own transfer function. And we want both of these transfer functions to be small. And since these are transfer functions, these are systems, we can do that. We can resolve the conflict between keeping both T and S to be small by making them small at different frequencies. So this is a very interesting point, and we will make use of this point quite a lot in this course. So if you take a look at this magnitude body diagram, we have system T and S. So their sum is always unity, always 1. So at low frequencies, S is as small as possible, and we have T to be very close to 0 dB, which means 1. And as the frequency increases, at some point they are equal to each other. And at high frequencies, this time T gets very small and S becomes close to 1. So what does this mean? So let's take a look at that. So at low frequencies, T is close to unity, and S is very small. Okay, so that means at low frequencies, T is very close to unity, which means for low frequency input signals, for low frequency reference signals, our system will have very good tracking performance. And at the same time, for those low frequencies, we also have this goal satisfied, which means the disturbance rejection is powerful at low frequencies. So the low frequency disturbances are rejected very effectively. On the other hand, when you come to the high frequencies, at high frequencies, this time T is small, which means we cannot track high frequency reference commands, which is quite fine because the reference commands are usually low frequency signals, right? So we don't usually want our system to track a very high frequency signal. So this is, in fact, we want it to be not respond to very high frequency commands. So that's also a good thing. And if you look at the sensitivity transfer function at high frequencies, it is S is close to unity. That means the high frequency disturbances will not be rejected as well as low frequency disturbances. So that means if you consider an aircraft, the disturbance can be a wind gust, let's say. So the high frequency content in the wind gust. So if you go into a very turbulent region of atmosphere, there will be high frequency disturbances there. So your control system will not be responding to that, but that's not such a bad thing because the dynamics of your system will be filtering those high frequency disturbances. So in other words, your system, your plant has certain dynamics and the plant dynamics will filter out the high frequency disturbances anyway. So you don't want your controller to actively eliminate those high frequency disturbances. So anyway, so we have this requirement that S and T, when they added together, should be equal to the identity. And instead of having them constant at all frequencies with some being equal to 1, you can make such an arrangement. So you make these transfer functions have different values, different magnitudes at different frequencies. So at low frequencies, T is dominant and S is very small, and at high frequencies, S is dominant and T is very small, and that gives you a very nice adjustment in terms of both tracking and rejection of unwanted disturbances and uncertainties. So we can already see in this chart how easily we can arrange or we can adjust robustness and performance properties in a robust control approach. Okay, so let's say if your goal is to have very good tracking, so you want to be able to track your reference commands very, very precise and very closely. So that will require you to make T as close as possible to identity at all frequencies. So in that case, you would choose T to be something like that. But that would require S to be something like that. And if you come back here, having T to be equal to identity at all frequencies will mean that T also appears in the sensor noise effect as well. So if you make T close to 1 at all frequencies, that means while you are tracking the reference command very closely, at the same time, the sensor noise will also go through, right? You will see the effect of sensor noise in your output and in your control system as well. But by its nature, the sensor noise is usually a very high frequency signal. Now, the sensor noise is either caused by electrical noise in your circuitry, or things like vibration through that can be picked up with your accelerometers. So they will also be high frequency signals as well. So at low frequencies, you don't really have too much sensor noise. So you don't worry about amplifying noise at low frequencies, which means you can safely choose T to be as close as possible to identity at low frequencies. But at high frequencies, you want to remove the effect of sensor noise. So if you know that your sensor noise is effective, let's say in this frequency range, you better bend the T transfer function such that this noise in that frequency range is removed. Okay. And in the future, we will have such frequency arrangements for against other type of uncertainties as well, not just for sensor noise and disturbances, but for other uncertainties in the system can be their effect can be removed by such frequency shaping techniques. Okay, so now at this point, I think we should make a review of this frequency domain analysis. So what does it mean to analyze the system in frequency domain? So we should review that part. But let me stop this video here, and in the next video I will start and I will continue with the review of frequency domain analysis techniques.